Hello all, welcome back to another lecture in the series of sensor arrays and imaging course. And this is actually a Fourier transform review as per request from some of you. And even if you know Fourier transform well, this you can treat as a sort of a refresher. The reason why I thought of spending some time explaining Fourier transform is because this concept we will be using it many times further. So it's important that you understand this. And if you're coming from computer science background, some of you might think that it's not really something which is relevant to you, but unfortunately that's not true. Unless you are going to work in very core software, at some point of time you will be using Fourier transform. Okay. Even otherwise also it's a very good powerful tool to know. Okay. So with that, let's actually have a very quick start. So this is not like an in-depth dive into Fourier transform or something like that, because that's not the objective. But this is the more of like an overview and trying to make you understand. If you really didn't know about such a transform, this is very important topic. So just like the name suggests, sometimes the name itself gives you some picture of what we are going to study about, right? So Fourier transform, of course, Fourier is Joseph Fourier, a very famous French mathematician. So he, of course, developed this transform, and as the name suggests, it is transform, right? So transform means you are basically transforming from one domain to other. So that is exactly the meaning of Fourier transform as well. We are trying to represent a signal in a more meaningful way. So we are going to transform the signal from the existing domain, whether it's time domain or spatial domain, whatever the domain which is the natural domain to it. We are going to transform that to a different domain, which is known as the Fourier domain. Some people call as the spectrum domain. In that domain, the signal will be represented with much more easiness and much more easy interpretation. Okay, so let's move on. So it all happened when Joseph Fourier was working to solve the heat equation. I'm sure those who have taken this course are well aware of an equation which is wave equation. And the only difference between or rather the major difference between the wave equation and the heat equation is like in the wave equation, the dependence of the u was actually to the second order of t, right? We were trying to derive that. But here, interestingly, the relation is actually the first order partial differential of u is related to second order partial differential of u with respect to the space. So that is something which is very interesting. So while solving this, he arrived upon the famous Fourier series. And what exactly is Fourier series is this. So if you assume a signal which is periodic, okay, so let's say s of x. So this is s of t is also fine. X is a independent variable here. So this can be x direction in space, for example. So if we have a periodic signal in space, that means there is a period associated with it. So period is nothing but the space period or the wavelength or the time period, whatever you want to call it. Okay, so what happens is actually outside of that period the same signal repeats. That's why it's known as period, right? It is periodic. So something like this. Okay, so you have, let's say, some signal. Let me just use the some signal which is having this shape, and this represents the period p. So if that is the case, then what happens is outside the period this signal just repeats. So sorry for my drawing, but I hope you understand, even here also. Okay, so the same signal will get repeated outside of this interval. So that is the meaning of a periodic signal. If that is the case, we have an s of x which is actually periodic with period p. Then what Fourier discovered was like this signal can be represented or can be decomposed into a sum of sinusoids, or rather sines and cosines, sine signal and cosine signal. So he in fact claimed that any signal s of x, okay, can be decomposed into this series of sines and cosines. So you take any random shape, if that is periodic, you can actually decompose. You can try to represent it using sines and cosines. So mathematically it looks a bit intimidating if you are really not a fan of maths, but it's a very beautiful expression. So what it says is like s of x is a signal which is actually a variation in space x in this case, or it can be space in time. So any independent variable, and some signal is a variation of that independent variable, and then if that signal is periodic, okay, with a period p, then you can represent that signal in a very beautiful mathematical model. So we are representing this phenomena. The signal is always a phenomena, right? That phenomena is represented beautifully as a mathematical expression like this. And what are these? It's not very difficult. This is actually a DC component, right? If you add any constant value, that looks like you are going to shift the signal up and down, right? That is the meaning of it, because all of us are coming from, you are all system on chip design people. So all of you are well aware of signals, the importance of signals. So when you add a DC component to a signal, what you are effectively doing is you are shifting the signal up and down, right? Up or down rather, okay? So A0 by 2 is exactly going to represent that. Any DC bias, any shift, so the signal is no more, if signal is centered around 0, this automatically vanishes, right? If when I say signal is centered around 0 is exactly this, okay? So if you have a signal like this is the 0, so it is centered around 0. But let's say the signal is something like this, okay? So in this case, you do have an A0 by 2, and that A0 by 2 is roughly maybe this value. So this value is corresponding to the A0 by 2. So that is the meaning of it, okay? So you do have a DC, so if there is no DC shift, automatically this expression becomes, this vanishes, this will disappear. And then interestingly, a DC component is there, the bias is there, and in addition to that you do have a series of cosines and series of sines. And these cosines and sines actually literally, if you go to this term, this is actually this entire term, if you want to consider, this is something like omega into x, right? So omega is 2 pi f. So n by p is something like the frequency of this particular cosine waveform, and similarly that of sine waveform, right? So basically when you change the n, you are literally changing the frequency of the cosine or the sine. So essentially this formula, very beautiful, one of the you could say the top equations in mathematics, which is actually saying you that you take a periodic signal S with a period P, I can beautifully represent that signal. I don't need to actually take the entire signal. I can just take one period of that signal and I can easily represent that using a sum of sines and cosines. And of course, you need to add a DC component to it as well. So this is something which is very important. And I would like to show you with this example. Okay, maybe let us start from the start. So let me just erase it. Okay, so essentially this is what I mean. So you have a signal which can be represented by a series of sines and cosines. That's what exactly you are seeing over here. So in the 3D direction you can see something like, yeah. So you have a signal and that signal can be decomposed into its components, and what you're seeing over here is these ANs and this is BN. Sorry, there is a small typo there. Let me just correct that. Yeah, so basically I corrected this Bn, that is not same as this. So An and Bn are the weights of these cosines that you will see over here. Okay, so yeah, so you see all these and then you will see weights over here. So these are the values of the cosines and the sines. This I am showing only maybe cosine here, but you can see over here. So these values, the magnitude of these are actually An and Bn. Okay, so any signal you take, actually I can represent. So this is actually the frequency axis, which is actually An and Bn values. I can decompose that into a sum of sines and cosines. So I hope it's very clear to all of you. Okay, so if you basically need an infinite number of such frequencies, that is the meaning of it. So you vary your frequency from minus infinity to plus infinity, then you will be able to approximate it. And then some of these frequencies may not be there. That's what you see a lot of zeros, right? They are not existing. But essentially this means that that particular square shape can be approximated or can be developed using these particular sine or cosine waves. That is the meaning of it. Now how to find that An and Bn is quite simple, because our objective is to find An and Bn, right? I have S of x. Now I need to find Ans and Bns. Then I can substitute in this formula and that's it, right? We find it out. So An is basically given by the inverse Fourier series, which is what this two equation stands for. So they basically is calculated by this particular formula, 2 by p, and within this interval. That's what I am interested in, right? Because this is a period. So within that interval I do this, I can get the ANs and the BNs. If I have ANs and BNs, only I need to care about those. So instead of this complicated square wave, I just need to store these ANs and BNs. I beautifully represented this S of x in terms of that. So that is the meaning. So there's not of, in fact theoretically there's a lot of applications of Fourier series, but that's not the case for us, because we may not be too much of interested in Fourier series because of obvious reasons, as you know, because this is a very strict assumption saying that signal has to be periodic, which is may not be that frequent in the case of practical scenario. A more generalized version of this Fourier series is something like this. Instead of splitting like cos and sines, you can actually put it in terms of a sinusoid signal, which is exponential signal. And please always remember, there is no magic here at this derivation. In case somebody is still figuring out why e raised to j term here, there is this famous Euler formula, e raised to j theta is equal to cos theta plus j sin theta. Okay, so from this formula only they are arriving this, because you do have cosines and sines and then you play with this. So this is a very easy expression to understand, right? So let's actually take a closer look at this formula. So essentially what it says is actually there is some signal and then you are trying to represent that signal in a complex sinusoid, that means cos theta plus j sin theta sort of representation. And then each of that cos theta and j sin theta, of course when n varies you have a different frequency sinusoid, right? The Cn stands for the weight of that particular sinusoid. So what does it essentially mean to you physically? So that means that my signal, maybe let's take a square signal, that square signal will obviously have different sinusoid components, and what is the value that I put or weight. So basically I want to put it this way, let's say some S is there, okay, and I want to put it actually in terms of W1 into X, let's say let me call some other name, let me just clear it off. Okay, so let's actually put this way, S is equal to some W1 and let me call it as X1. X1 is your first frequency sinusoid, plus W2 X2 second frequency sinusoid, W3 X3 plus so on up to infinity, right? So basically my S I'm going to represent in terms of 1, 2, 3 etc. sinusoid. That's the meaning of it. Okay, so I hope it's pretty clear to you, this part. Okay, so that is the intuitive understanding of it. Now let's move on, because this is not what we were talking about. We were talking about Fourier transform, right? But as I said, periodic signal is a very specific category, right? And that may not be existing all the time. We need to generalize this for a non-periodic case. When I say non-periodic case, is like the signal is really not repeating. It is coming and going. It may be dying off. Okay, so that particular version where we extend this to non-uniform or non-periodic, not non-uniform, non-periodic signals, that is known as Fourier transform, okay, or very strictly known as continuous Fourier transform, because your time or the space axis is continuous. Okay, the x or t, the signal is continuous, there is no discretization happening. That's what happens in the natural world, right? So this is the formula. It is much more easier for you to understand. So you have the Fourier transform S of omega. Okay, so here I put as time because that is easier for us to visualize rather than x. But this can be S of x e raised to minus j omega x dx. Perfectly fine. There's no problem. You should be able to generalize this. Need not be time. Please remember that. Some people have that confusion. It need not be time. It can be space. Whatever dimension. You find a signal which is varying with that dimension. That's it. Okay. So in this case also time varies from minus infinity to plus infinity. This is your S of t, which is a continuous signal, and e raised to minus j omega t. So here it's very easy for you to understand as omega. So basically this is for each omega, right? So S of omega is your Fourier coefficient, that Cn, Bn values that we were talking about. So you change omega, you start from omega equal to 0. And then you go, or rather we can say this is ideal case, right? So omega is equal to minus infinity to omega is equal to plus infinity in whatever resolution you want. You do that. For each omega you substitute that omega here, okay, and then you do basically this operation and then you sum it over the entire duration of the signal, and that value, that single value will be your coefficient corresponding to that particular frequency. Okay, so this is the operation. Now, if you're coming from communication theory background or with interest in communication theory, what is this term actually means? Forget about the integral or all these. What does this term means? S of t e raised to minus j omega t. So this is something like a demodulator, right, with omega. So basically you are trying to make, you are multiplying the signal with a frequency with a sinusoid which is actually centered at omega. So basically any component in this particular signal which is at omega will come to 0, DC frequency. So that is the meaning of it. So let me take an example to, let's say S of t is equal to, let's take again complex signal for easy explanation. So let's say it is e raised to j omega 0 t, and then let's take omega equal to omega 0 here. So then this becomes e raised to j omega 0 t e raised to minus j omega 0 t, right? And then of course we know that this will become omega 0 minus omega 0. So that becomes sort of 0. So there is a DC component at 0, right? So there is of course an amplitude. So that if I take with an amplitude a generalized scenario, sorry, it's not, I don't know what I did here. Okay, so what you actually have it is a e raised to j omega 0 minus omega 0 is 0. So this is a. So you have a DC, you basically whatever was this component, now actually you made it to, by doing this operation you made that component as the 0th frequency component, and by that you eliminate that particular frequency, effectively you get the amplitude. So what is that component, right? What is that value? What is that signal value? What is that what you call when you try to see an omega 0 component, how much of it is available in the signal? That is the meaning of it. So if you can also treat this way, and then interestingly, once you do this operation, you will come to basically the low frequency, right? The 0th frequency. But this is a very ideal scenario that I put. If you have some phase component here, let's say some phase component here, so then what happens is this will not be exactly 0, because that omega 0 t will actually get vanished. But then yeah, so if there is a phi component, this will cancel, but that phi component will remain here, e raised to j phi will remain here, right? So that is the problem. So for that, then we may not be able to get a directly. So how do you go about it then? You may have to actually do an averaging, right? You just do an averaging on this result so that the phase may be random and it gets cancelled out each other, and you find out the A together. So that's exactly happening here. So when you sum it up over the entire duration of time, so basically whatever the t component, j phi t, whatever the component is, the phase may not be constant. It may vary with the time t. So that component, if you do an averaging on this particular thing, you end up in getting the DC value, right, most of the time. So that is exactly happening here. So just to reiterate, if I'm confusing a lot, just to reiterate, what we are doing actually is we substitute omega with different frequency values. By that way we create different sinusoids, and then we sort of demodulate or multiply these two. What you get is sort of a DC component or a low frequency component, and then if you do an averaging, then you eliminate all the high frequency component to make sure that you are not considering any non-wanted components, and you get that single value out, the amplitude value out, the corresponding value of the presence of that particular frequency in your signal S of t. That is one way to look at it. Another way to look at it is something like, if you are very fan of correlation, you can think of something like your signal is correlated with that particular frequency, and whatever is that correlation value is what you are getting. So if you see this expression, it is something like correlation only, right? So you are basically putting a signal correlation with 0 lag. There is no lag here. You are not going to shift the signal left and right. It is at t equal to basically 0. Sorry, tau is equal to 0. In your correlation expression, you have a shift term, right? That term is 0. So this is like 0 lag correlation. So you're going to correlate your signal with a particular frequency component, and that value is basically your Fourier coefficient. Okay, So that's it. Then you change another omega 0, you do the same operation. So you vary omega from minus infinity to plus infinity. For each of that omega, you find the S of omega value. And then if you plot the magnitude of that, again, so this is omega. Of course, it goes from minus infinity to plus infinity. So each of these omega, you plot the magnitude values, something like this. That is what you get in the Fourier transform. Okay, so instead of the signal S of t, which may be continuous in time or so much of variation in time, you are going to represent it in terms of the Fourier transform. Ultimately, you get something like this. And this, each of these values, so these are frequencies, these are the variations of omega, right? Omega 0 or whatever value you want. And then these values are the magnitude which corresponds to the correlation of that particular frequency. I hope I'm not confusing. So whichever way you want to look at it, it's as simple as something like you are trying to represent your time or space signal into its frequencies. Okay, so you're identifying that. And then of course this is Fourier transform, inverse Fourier transform. So if you have the S of omega, you need to know how to come back to S of t. That is actually given by this. Just only major change that you see over here is only in this particular thing, right? The sign is inverted. And then of course this is omega space, so you have to have the integration in omega, and here it's time space, so it is in time. That's only difference. Now there is a problem again here. This is continuous time, and then imagine that you are doing implementation of a Fourier transform in an analog system. It's almost impossible to do, right? So you need to go to digital system, and you should not worry much, because there exists definitely something known as discrete Fourier transform or discrete time Fourier transform to start with. So why discrete time Fourier transform is because now t is no more continuous. I am going to discretize my t. So t will be something like nts. So n is a number and ts is the sampling rate. So what is all this nonsense means? Let's actually take that. So this is my signal, let's say, okay, and then I am going to sample this at uniform intervals of time. Let me use another color, okay. So I am going to, so this is my time axis, let's say, okay. Now I am going to take only certain values, only these values, okay, and so on. And then this time interval between each one of them, between each sample space, that is actually Ts. We call it as the sampling rate if you are very particular. And then of course this n is basically, you start with n equal to 0, that is this, then n equal to 1 means Ts, that is this, then n equal to 2 Ts is this, 3 Ts is this, 4 Ts is this, and so on. Okay, so by doing that, basically it's like your ADC, right, analog to digital converter. So you basically you replace T by NTS, this became a digital signal. So no more a continuous integral is required, the integration becomes summation, and then the expression for the discrete time Fourier transform is omega. Instead of just to distinguish, we put it as S of f, because the moment it comes to Fourier transform, it is more about that frequency, right? Frequency in terms of number of samples per cycle or cycles per second and so on, right? So that particular frequency is this. And here again I am trying to sum it from minus infinity, that is infinite number of samples, which need not be required, but let's assume for the generality, let's put it this way. So S of n is your discretized version of S of t, or you can actually even put nts instead of S of n, we can actually put nts for the completeness, because that is what exactly it means. Okay, so then rest of the things are same. There is no dt because this is summation now, and then you can see over here I just expanded omega to be 2 pi f. Okay, so this is the center frequency of the sinusoid that you are going to create. N is basically the number of sample, the n sample, which is actually going here, and then Ts is the sampling rate. So this is quite straightforward. I hope there is no confusion here. And then similarly the inverse is actually given by this. There is no difference except that the time is discretized. Now if you understand the concepts of sampling and sampling theorem and all the things, one important change that you can actually envision is this is actually now discretized in time. I think we definitely have a session on sampling theorem probably coming up, so by that time you will understand what I am going to say. But even otherwise, I think even the sensor arrays thing, we will derive the sensor array also in a similar fashion. Okay, so you will come to know about it. So what I am saying actually is, if let's say I have S of t, if I take the spectrum, if I take the Fourier transform S of omega of that and then plot it, it may have some shape, let's say. Okay, So S of omega, and let's say this is minus B and this is B, the bandwidth. Okay, so this is in frequency, so this is omega, so this is S of omega is something like this. The moment you discretize that signal, what you are going to see is the same signal will be there definitely, minus B to plus B, but then the signal will get replicated. In this case there is no replication, there is one spectrum and that it dies out, for example. But in this case, what is the moment you do that T is basically sampled at n Ts, what is going to happen is the same signal will get repeated at different locations, and these locations are not random locations. This is 0, this will be Fs, this will be minus Fs, you will have one more at 2 Fs and so on, and this Fs is nothing but 1 by Ts. So this is frequency, that is inverse of your time Ts, the delta NTS, right, the Ts. Okay, so this problem is there. Okay, so this is very important. This is not highlighted here, but this is important to understand, and you need to actually keep these guys apart. The images, we call it as images of this particular thing, that you need to keep it apart, and for that actually you need to what is the way to keep these guys apart? The images apart, all these guys actually. So this is what we are interested in, but these images should not overlap with this, so you need to keep this apart. So that means intuitively from this axis you can say that Fs has to be very, very high. Okay, so Fs has to be very high, higher than, so this Fs, okay, so this we already know, this is minus P, this is plus P. So how much closer you can come? So how much closer this guy can come to this? So I can move it so that this minus B comes and sits here, right? So something like this, right? So then what is that Fs? So Fs will become B plus minus B. So Fs should be at least greater than 2 times B, and this is a very famous equation that is actually known as the Nyquist criteria. Okay, Nyquist theorem rather. I think something is wrong with my pen, I'm sorry. So hope you might have studied about the Nyquist theorem in at least in one of the digital systems courses. So that's not really a topic of discussion for this session, but I thought I'll introduce that here so that it's a bit clear to all of you. So that's it. I hope everything is quite evident here. And in fact, actually this is there's a small typo here. Let me just correct it and then explain it. Okay, so sorry for those typos because I want everything to be crystal clear to you. So I just added the TS here, so that's very clear that T is discretized into this. And then of course Fs is nothing but 1 by Ts. Okay, so that's the same. So Fs is a sampling frequency. So as the graphic representation I was showing you, that is the point where the things get replicated, the images get replicated, and you want that Fs to be as far as possible. So if you want a higher Fs, Fs is nothing but 1 by Ts. That means you are basically the interval, the sampling interval has to be narrower. So if sampling interval Ts becomes 0, it's what is going to happen is like you recover the original analog signal, right? Because you literally take every other sample in the analog signal. That's the meaning of it. Okay, so forget all that if you're not keen. Just important is you discretize the time. So you have a discrete time Fourier transform, and it is given by S of f is equal to this particular expression. Again, ditto same. The understanding should be same. You are correlating your signal with a different frequency altogether. So as the n value changes over here, your frequency is going to change. Okay, so that is the meaning of it. Sorry, not n, f value changes here, frequency is going to change, and n is nothing but the sample number. So as n changes, you are taking the full extent of your signal. That's the meaning of it. So signal correlated by a particular frequency, that value will form the S of f. Right, similar to that, you can take inverse Fourier transform as well, which is here. Now there is a problem here. If you notice, your frequency is still continuous. Frequency is not discretized. Your time is discretized, but your frequency is still continuous in this case, and that is the reason why we gave a specific name, discrete time Fourier transform. Okay, so its time is only discretized. Now but then the problem is you just think about the inverse Fourier transform calculation in the computer. That's not possible, right? Because your f is actually not discretized. So your f is still analog in nature. So to avoid that, you discretize f also, and that is what the popular discrete Fourier transform is all about. So once you discretize the frequency as well in addition to time, that means instead of f, I will divide the f into, so you know the range of f. Okay, so that's the interesting concept here. Let me just make it very clear. So the range of f we already know. That is what this is about, right? So f is basically from minus fs by 2 to fs by 2, or some people even consider it as 0 to fs, whichever is fine. Okay. So within this range, it was continuous. The frequency was continuous. It would have taken any value that you can imagine between this range or this range. But that's very difficult for us in the case of a computer. So what we did is, so let's say f is a vector which is actually ranging from 0 to fs. We divide that by some number. Okay, so that is how we discretize the frequency also. So but then the problem is, the moment you discretize the frequency, the assumption the same as when we discretize the time, we found that the spectrum is replicating, right? So similar to that, when you discretize the frequency, your time also will get replicated. That means whatever is the duration of this time, okay, so that outside that it is seems to be replicated. So that is important. So that is again coming because whatever you do in time, it is dual in frequency, which I told many times, right? So similar to that, when you discretize in frequency, you are basically making the time actually having an issue. The time will get also replicated. So that is a very fundamental expression. So fundamental condition in discrete Fourier transform, that when you take discrete Fourier transform of a sequence, okay, the fundamental assumption is that the sequence is actually repeating outside its consideration. So let's say you consider a small n samples, okay, in the signal. So then when you take discrete Fourier transform is assuming that the signal is replicated. So what I am saying is, let's say you have, let me just make it very clear. Okay, so you have some signal, some random signal. Okay, and in that I am going to take Fourier transform of only a small region of it. Let me just mark that. So let's say this is the region I am going to take Fourier transform. So I put this out and then take the Fourier transform out. Then the Fourier transform thinks that the same signal is going to get replicated. Let me just okay, so same signal basically this particular signal itself will get replicated here, everywhere. It will be like that. That is assumption. So it won't be seeing these variations in the signal. It assumes that this is the signal because that is the same, just like discretization in time created replicas of the spectrum. Discretization in frequency gives replicas in the time domain also. So that's a very important thing. Many people tend to forget about that. Okay, so that is why it's very important to have that concept in mind. And another important thing I want to make sure that you understand is, there is this popular concept fast Fourier transform, FFT. Okay, so fast Fourier transform is not another Fourier transform. It is just an efficient way, an accelerated way to implement discrete Fourier transform. So fast Fourier transform is just an implementation of discrete Fourier transform. So don't get confused. So for example, when you do discrete Fourier transform in MATLAB or Python, you make use of fast Fourier transform. So if somebody is interested, please see how that efficiency, how that implementation efficiency is happening. Okay, it's a very interesting concept. Okay, so going forward, so when you discretize in frequency, this is what going to happen. So you're basically discretizing the frequency. That basically normalized range is actually 0 to 2 pi. So outside of that, 2 pi is going to repeat. So that's the meaning of it. And then the 2 pi is getting divided into n divisions. So n is the number that is going to divide your frequency. That determines your frequency resolution, 2 pi by n. And then k is the factor which is actually changing the frequency. So you can see it here. So now it became something like truly number. There is no physical frequency or any physical time into this picture. This is completely numbers. K is a number, n is a number. When n changes, you are actually sweeping in signal, and when k changes, we are sweeping in frequency. So for each k, you have a different frequency signal generated, and then you are correlating with the entire time series, and then that single value will form the k. Okay, so this is a very beautiful journey, and similarly the inverse Fourier transform is also there. So you started off with Fourier series, then we realized that Fourier series is not applicable because everything is not periodic. So then we extended that to Fourier transform, where non-periodic signal is also considered. But then this is not discrete in time or frequency. So we can't do any computer calculation using that. So computers, if they want to use it, we have to discretize, we have to make digital. So you discretized in time, it gave discrete time Fourier transform. And then we realized that inverse Fourier transform is not possible by using computer. You have to discretize the frequency. So then you came to discrete Fourier transform, which is what we use in computers. And in computers, we make use of the fast Fourier transform because that is how we can implement the system. Right, in computers, it's much more efficient to do. Okay, so that's it. I hope it's pretty clear to you, but don't forget the underlying major principle, which is actually what? Which is nothing but Fourier transform means you have a bunch of sinusoids. The sinusoids are nothing but sums of sines and cosines. They vary in frequency, and each Fourier coefficient, the meaning is like each Fourier coefficient corresponds to a frequency waveform, and you are correlating your signal with that waveform and finding what is that correlation value, and then you put it. So that is what actually Fourier transform is all about. So if you are coming from the computer science background, and you might have heard about the basis functions. So basis functions are nothing but you are trying to project your signal onto, you are trying to represent your signal using some basis functions, right? Weights of the basis functions. So if you think from that perspective, Fourier transform is nothing but you are trying to represent your signal using basis functions which are sinusoids. Simple, okay? So if you think that way. So I thought of explain from different viewpoints and hope you are able to understand this. And we will have a MATLAB demo of this as well in quick time so that you understand how to use it as well, okay? So just to reiterate, we have continuous time Fourier transform, which means the signal is continuous both in time and frequency. Then you sample in time. Basically sampling in time can be represented by concisely using this mathematical formula where x of t is your analog signal, and then you are going to do a delta function. Basically at different NTS values you take the amplitude of this signal. That is the meaning of this particular expression, right? And then once you discretize it, it becomes discrete time Fourier transform, and then you discretize in frequency, it becomes discrete Fourier transform. I hope now onwards, even if you are coming from computer science background, you should be able to tell somebody else, explain to somebody else what is this fine line of division. And for us who are living in the digital world, we only care about this guy, right? Sorry, only care about this particular guy. Okay, so now let me use some pen and paper and then explain to you some of the interesting derivations that we come across. So let me just open the whiteboard. It's slightly long lecture, but I hope you don't mind that, because it is actually something which is very interesting, right? So maybe I'll stop the lecture now, and then we will put the next lecture on some of these derivations in Fourier transform, interesting derivations in Fourier transform, because I told about the Fourier transform of a impulse response is like a wide spectrum, or Fourier transform of a rectangular or a square function is a sinc function, and all those things we discussed, right? So we will come to that in the next lecture, okay?